So, good afternoon, everyone. Hope that you can hear me okay. Please, and we hope to manage this hybrid meeting in a good way so that everyone can participate. So let me know if somehow you are experiencing some trouble in hearing me or any one of the presenters today. Okay? So, for this breakout session, we want to present to you the development and the vision that the project and the partners developed for the smart and flexible distribution network operation, and explain to you what we call the multi-level preventive management framework that in the end wants to help the DSO to interact with the market, to be able to identify flexibility needs, to select bids, to validate, and so to interact with all the process involved for the flexibility service procurement. And then we have 3 dedicated presentations to the low voltage network flexibility because we consider it as a key issue to unlock the use of flexibility from the low voltage resources. And so we will present to you 3 different approaches for the operation of tools developed to improve the observability of low voltage network and allow the use of the flexibility. And finally, the discussion and closing, where we have prepared some questions, also to allow you to participate through some online questionnaires. But I also invite you to raise your hand and participate with us here today in the room, because you are a lot more online than here today in our room. So please participate through Slido. You have here the code of the event to participate. And so I ask you and I give you some moments to connect and to be able then to answer to the questions.
So this is the question I think we're talking about.
So people that are doing also and we have one. Okay, so let's move on, because in the end we have a lot of information to try to tell you a bit about the developments here in university. So, in terms of the vision of Universal for the distribution network, we believe that the network needs to be flexible, predictive, and resilient. Flexible, enabling the participation and the active participation of distributed energy resources. Predictive in a way that you can also, and it should be able to identify a priori and forecast technical constraints, and also quantify the flexibility needs for the next day or the next hours, or even for the next months if we are talking about network planning. But also resilient in a way that it can improve its self-healing capabilities, also with the participation of these flexible resources. Today, we will focus mainly on the flexible and on the predictive. We hope that the next workshop we can focus on the work that we are doing to improve the resilience of the network. These tasks are ongoing, and then on the next workshop we will be able to show you the results and the capabilities of the tools that we are developing. And so, as Pedro showed you in the introduction, so we have defined a set of flexibility services considering the DSO needs. And today we will focus on physical congestion, control of voltage violation, and on the phase balancing needs. And so we will mainly talk about corrective and predictive congestion and voltage control. And so, as I was saying, considering the different steps of the market process, and so from the registration, needs assessment, procurement, activation, and then validation and settlement, the DSO will need to adapt and create and adopt the necessary tools to be able to interact with the market platforms and send and receive and select the necessary information. In EUniversal, we are focused mainly on the needs assessments, the procurement, and the activation. And so we are talking about tools that allow to forecast technical problems at the high voltage, medium voltage, and low voltage network, quantify flexibility needs or optimal bid selection, depending on the market design, and so also allow this interaction with the flexibility markets, platforms, and aggregators. And so we developed this multi-level preventive management framework divided, as I told you, in these 3 steps. So we have a set of tools for the network state and constraint forecasting, a set of tools for the flexibility needs assessment, and for the flexibility selection and validation. And you can ask, why should we have so much tools? Because some of them have different approaches, also considering the characteristics of the pilots, and so they are somehow complementary, and they will allow us to demonstrate that based on different availability of data and network characteristics, we can adopt different sets of tools. And if we go to network and state forecasting, so as I told you, we are trying to forecast and identify potential voltage and congestion violations. So this requires accurate load and generation forecasts for the high voltage, medium voltage, and for the low voltage nodes. And here we have some challenges. For the high voltage and medium voltage, conventional power flow algorithms can help on this identification. The main challenge here is how we will do this for the low voltage network, considering that forecasting has low resolution for every node, and so the error can be higher. We typically have poorly topology and characterization of the network topology and electrical characteristics for these low voltage networks, and we have limited monitoring and communication infrastructure. And so, besides the typical characteristics of the low voltage network that is unbalanced with single phase loads, in addition to that, we have low automation and monitoring capabilities. So for the high voltage, besides the conventional ADMS tools, so the power flow, the OPF, and so on, in the Polish demo, we are demonstrating dynamic line rating as a way of updating the line capacity, and this is good for detecting congestion, but on the other hand, to determine if we have additional capacity to integrate renewables. And so we are testing a kind of service that the DSO can offer to the renewable power generation plants. If we go to the network state and constraint forecasting for the low voltage network, we here are taking and we are proposing a set of data-driven tools based on smart meter voltage and load historical data, on incomplete low voltage grid topology, and on typical load diagrams. So to try to increase the observability of the low voltage, I will not go further because then Gilles and Koen will present. I will give a presentation of a more based more on conventional OPF, but that also considers this uncertainty and this limited information. Okay, so if we go to the assessment of the flexibility needs, so we assumed that probably instead of just collecting the bids from the market, we could also pre-identify the flexibility needs. So where are the problems and what is the quantity that the DSO requires to solve the problem? This concept of flexibility areas or zones is something that is typically adopted in the market platform design. You have this also described in market-based frameworks such as USAF. However, these congestion zones will vary according to network conditions. On the other hand, these market participants and considering the local nature of distributed of distribution technical problems, we have proposed here a dynamic definition of these areas, and on the other hand, try to coordinate between the different voltage levels. And here we have also two different approaches. In the German demo, we propose a bit more simple approach, starting from the low voltage to the high voltage, but addressing the redispatch and so the coordination with the transmission system operator, based on this estimation of the flexibility potential or the headroom in the substations, and we'll also talk a bit on this. On the Portuguese demo, we are taking a bit more complicated approach because we are starting from the medium voltage network. And so we are saying that maybe some of these problems on the low voltage can occur due to medium voltage problems. So let's try to solve them first and then see if we still have a problem in the low voltage network, then we will try to solve it and add additional flexibility to this. And as I told you, we have this concept of the dynamic flexibility zones that in the end is basically to determine which is the set of nodes from the low voltage network and from the medium voltage network that can effectively solve the technical constraint. So, for example, if we have a problem in a low voltage feeder, it does not make any sense to consider flexibility from other feeders. On the other hand, maybe we could also, instead of going to the end of the feeder or to the specific node, we can extend this area and allow the different flexibility service providers to participate according to their technical efficiency, let's say, and then the market will decide about the cost. And finally, for the bid selection and validation, and in this case, we assume that we can collect all these bids from the market without sending any bids and selecting this bid. And so this will be done by the DSO. You can see here two different approaches. One approach where the market platform collects all the offers, and then the DSO decides which offers he wants to select with all that information about topology and so on. On the other hand, we have here an additional step where we send all these needs or these somehow the needs and the set of devices that can help solve without causing additional problems and let the market decide. And so, in conclusion, so we are developing this coordinated management of the distribution network, trying to coordinate medium voltage and low voltage network, and even with the transmission, considering the redispatch points here in Germany. But we need exactly to have this effective design on the tools, considering also the markets and the processes involved. But we consider that here the key point to enable all this is to have adequate tools for the low voltage network. And this will be the point of the other presentations. And so, to conclude and to involve here some interaction and try to wake you up, I would propose you to respond to the following questions. So, considering that we have here a lot of participants from other projects, and also to try to do the right questions to our audience, I will ask you to answer to the poll. So, which kind of tools your project is focusing on, or you think are more relevant? So, okay, low voltage network. One.
It's only one answer.
Yeah. Let's wait a bit more. At least the ones here need to respond. Okay. Let's see if we have just one. Okay. Okay, so most of you consider this coordination between the TSO and DSO the most relevant, followed by distribution network planning and the low voltage network. This is actually interesting.
There's a fact.
Yeah, between the planning and the low voltage network. Interesting. Okay. We will focus down on the low voltage. Sorry to the guys from the TSO, DSO, we can leave it throughout the session. But at least this also allows us, I mean, there is no flexibility from the distribution network. Also, we need this low voltage to do that. Okay, so next in the agenda, we will have Mark presenting the low voltage flexibility need assessment tool. From the tool is being developed by the team and by the team of A11. Then followed by from that will present the low voltage congestion forecasting, and then from INESC TEC, Jill will present state estimation and voltage. So, yeah, please.
Thank you, Clara. So the idea of low voltage needs assessment tool is to quantify the distribution network need for flexibility in order to mitigate probable events that can happen. So my presentation is divided into two parts. First, I will describe the tool, quantify the technical innovation, clearly state the inputs and output of the tool, and possible features and capabilities of the tool. And the second part is how this tool is going to integrate with the German demo for which we are developing it. So the needs assessment tool is providing DSO with recommendations that what is going to be the distribution network flexibility needs in a day ahead setting. And what we consider is future uncertainties, probable network congestion, and also that distribution network imbalance. So it's crucial that activation of flexibility solves traditional congestion issues, at the same time does not create imbalance issues, which is also probable because most of the loads, especially in the German case, where we observed that for the three networks, more than 80% of the load was single phase. The connection was single phase, which means flexibility derived from such users will be single phase, and it's crucial to consider imbalance in such a setting. The output of the tool is going to be day-ahead flexibility needs assessment. We are also trying to extend it to give recommendations on the bid selection aspect. So how the scenarios are being generated is we are creating a multivariate distribution, and we are decomposing and creating 100 scenarios because of the time constraint in which the tool needs to provide an output. And since we cannot design our system for worst case scenario, we are applying robust chance constraint. I'll briefly describe for those who are not aware. So the inputs of the tool are, so these separate blocks are operating independently. Scenario generation block, for example, it takes as input as nodal load forecast and historical forecast errors, and provides you with a bunch of scenarios, which goes into this flexibility needs assessment OPF. And this OPF will provide us with an output of temporal and locational needs of flexibility. And all this data is then condensed into nodal and zonal flexibility needs assessment. And for zonal flexibility needs assessment, we are clustering the distribution network in a manner that we have a connected cut in the graph, so that only the neighborhood points are in the same cluster. And this will help us in identifying for the DSO, for example, for providing alternate resources. For example, you have certain beds and you have a needs assessment. In most of the time, the needs and the bids will never match one-to-one. And in that case, you cannot run hundreds of power flows again in order to identify which of these resources should be procured in the day-ahead setting. I present here a numerical example in which you have 76 nodes in the distribution network, and the heat map, on the first heat map shows you the nodal flexibility needs assessment. So this network was intentionally designed with a lot of PV and a lot of load. So you have congestion in this network, and you see that there are like load curtailment happening during the night and late in the evening, and generation curtailment is happening during the day. And when we try to reduce this network into zones, so we create a partition the distribution network into 12 zones, and this is the manner. And most of these flexibility needs that we observe are having a very intuitive explanation close to the end of the branch or end of the feeder where these needs are happening most of the time. So we are providing here a distribution network data-driven tool which provides you how much flexibility will be needed. And then extending onto the idea, so you have the needs, and now suppose we have the limits, then we can provide which of these, so this is an extension of the tool which we are considering. This is an ongoing work in which we provide DSO with a recommendation on a network which is driven by network state and not the market. So maybe both, there can be a bargain between both of them, which will provide in making more effective decision making. Okay, so when we design in robust optimization, we design it for the worst case. In this case, suppose we design the flexibility needs assessment for the worst case, it will be gravely over designed, and the flexibility procurement will be much higher. So in order to reduce this risk, so DSO might be able to take the risk of removing the flexibility needs, which are targeting the extreme tail events of the needs. For example, you have ramp up and ramp down needs, and if we eliminate the last 5% of the flexibility needs, it will reduce significantly. For example, in our simulations, we have observed that this will reduce more than 50% of the flexibility needs, because extreme tail events are happening in very, very rare situations, and this mitigates very few congestion incidents. And this will also help us in prioritizing that which incidents are more crucial or which procurement might be more essential for the DSO in order to mitigate congestion. And we also provide, so we define this as a risk of DSO. In optimization sense, it's called chance constraint. And we also provide a mechanism to tune this chance constraint in a sense of a bargain, that you have to bargain between the amount of flexibility you procure and how many congestion incidents it's probable that you won't be able to mitigate. And yeah. Okay, so broadly, these are the capabilities. We provide a temporal and locational means of flexibility of our distribution network in day ahead. This means mitigates the probable thermal overloads and in the distribution network. Also, the voltage limit violations are mitigated. This also considers the voltage imbalances of current and voltage. We then extend this nodal needs assessment into zones. This tool inherently takes into account the reactive power. From the numerical simulations, we have observed that reactive power flexibility is very crucial in distribution networks where the power factor is low. And we present a novel network-driven flexibility activation signal, which looks very similar to locational marginal prices, and this can also be generated in a distributed fashion. Okay, moving on to the second part, how we are going to integrate our tool in the German demo. This gives a broad outline. So all the greens are input, green blocks are the input. We have some processes, for example, load mapping, and the key functionality, of course, is the three-phase flexibility needs assessment. So you can see there are a bunch of other blocks. For example, we are right now working on phase estimation, because in the German setting, we do not have exact phase information. But, and actually, we don't need exact phase information for all the things, but we need exact phase information for flexible resources where they are connected. So if we have that information, I think that will be enough for our tool, and we are trying to build that tool for now. And if we have the limits for flexibility in the day-ahead setting, like what flexibility is available where, maybe we can also make our decision even further better. So this will be our outline of the tool. And for in the German setting, we are building Dockers, which will be through which we will be able to implement our tool on the German server. And since the tool is using diversified blocks, we have created two containers. The first container parses the network and provides the scenarios, and then it dumps all these data in a volume on the server, which is picked up in the second Docker, which provides you the output of needs of the distribution network. We were able to have some publications and some ongoing work. So these are most of the papers which are complete or under review, and there are some ongoing works which is not mentioned here. Yeah. With this, I would like to conclude. Thank you.
Thank you. And so here, Umar presented this tool that in the end can actually, besides the active power flexibility needs, it can also address the active power. And it can also minimize the total components because it takes these characteristics. The detail is that you need to have the topology characterization, at least you could have some parents, but you need to consider it.
Topology by phasing.
Yeah.
So we have
Identification of the space, of the network characteristics, and so on.
So the German phase thing is very interesting, is because most of the work, almost 100% of the work on phase estimation is with smart meters. But the demo network that we are working on has 0% smart meters. We have some measurement boxes distributed on the distribution network, and we have a few measurement home energy management systems. And now, how do we use this kind of setting in which you have not even a black, white, and gray box? It's like almost 10% observability in the distribution network, and we will try to see how our algorithm works. We are collaborating with that with Witness in this work.
Okay, thank you, Mark. So we will see now from the presentation from that in the end, having this limited data, with that we hope also to be able to estimate and to forecast the congestion in the low voltage network. So please.
Yes, thank you. Clara set forward this tentative title to me, Improving Low Voltage Observability with Limited Data. And I decided to keep it because I was a bit intrigued by it, because when we talk about low voltage observability, what does that mean? What is this challenge? And we have already had quite a few components that popped up, but I think it's very well to stand on top of it and think about this challenge that we are facing. And then that also explains a bit why we need all such novel and more advanced tools to deal with it. And when we talk about the voltage grids, well, first we need to look at how it looks. And change. Yeah, this is the low voltage grid. This is how it looks. Well, I mean, first, of course, this is not low voltage grid. This is a grass meadow, but it's an excellent analogy to get a mental picture of the complexity of the like the low voltage consists of thousands and thousands and thousands of small, nearly independent systems, cross-links, feeders. But what you also have is that they all look kind of alike. You will find no two identical. That's also complexity we need to deal with. There's a big difference where the analogy breaks. If one of these late litters, there will not be angry customers calling to the farmer to complain and advance. So we need to keep all of them healthy. And that is what observability in low voltage means. This whole field of blades moving gently in the wind, and we have to be aware and have a good sight on the health of each and single one of these blades. That is the level of challenge we're dealing with. And the DSOs, they're always looking at the low voltage grid, just doing some kind of putting cables and no, we do this. A bit more specific. What does that mean? Well, there's a massive scale. Of course, every feeder is unique, as I said. It's not only unique, it's also a linear system. We have limited measurements. We covered it already. Real-time measurements, perhaps few, perhaps none. Measurements on every connections, probably never. The grid data is incomplete. We don't know the phase. It's often inaccurate. And on top of that, we don't deal with nice predictable industrial installations. No, we deal with human beings, and human beings tend to be largely unpredictable. We've dealt with this in the past, if we forget, we indeed just put big enough cables in the ground, which are big enough to write every peak forget about it. But as I told you, to explain to this audience, with energy transition, implication of heating and transport, demand response, this is becoming very expensive to need. The load is going up, but also the synchronicity is going up. So we need new solutions. My name is Breakout Session. I work for Vito and and I work in the team that works exactly on this class of problems. And we do that by combining on one hand science classic power system engineering, but we enrich it with artificial intelligence science technique, specifically to be able to deal with this environment of large scale, scarce data and high uncertainty. And using these techniques, we work on a whole range from getting a better view of what's in the ground, to find out which is on one cable, to large scale simulations to ensure that our installation is effective, to look how we can better use and optimally use our current assets, etc. and so forth. But the most challenging thing at the end of the line is the information chain. Can we, from the low voltage grid, offer some useful information of the state of the grid such that it can be used to safeguard the grid and user experience. And that's when I get to what we're doing in EUniversal.
Could be that you have to speak up louder.
Louder. Okay, I'm going to stand. Wait, this is
The mic there behind.
Sorry?
The mic is behind.
That is the mic. Yeah. Okay, so I should speak in that general direction. Okay. So I can't look at you. Now finally meet physically and now I cannot look at you. Okay, what we're doing in EUniversal is a tool that we deploy in the German pilots with our colleagues from Headroom in their grid. And it's a tool that makes a congestion forecast for the low voltage grids and then transforms that information into something that can be used by aggregators market platforms. We call it the Pyhtia tool, by the way. Pyhtia, that's the name of the high priest, or was the name of the high priestess of the Oracle of Delphi. So that's what we're trying to do. Predict the future, predict mayhem and congestions. There's a whole pipeline to it, and I'll quickly run through it to all the components. You have a bit of an idea of how it works. And it all starts with what data there is. What data there is on one hand side grid data, topology, electrical data, type of cables, length of cables, etc. and so forth, which is incomplete, as we know, because for instance, we don't know which houses on one phase. We have profile data, but as much said, we don't have vision to deleted data in German market. So we need to fall back to a database of historic profiles or our data collected elsewhere, from which we need to sample and model connections which are in the grids that we consider. We do that, it's a forecast based on weather information because the load in the grid is influenced by solar radiation and temperature, so that we take note. And then finally, pilots is all about flexibility. So we also take some information from the flexibility, but it's limited. It's the location of the devices, the rated power, and their type. And that's what we need to make it. So the first step, what we do with it is a statistical power flow. We could do an exact power flow, but that will never work because load uncertainty. So we've developed a statistical power flow for specifically for the low voltage grid. That means it has to be three-phase. System. It means it has both active and reactive power, etc. Transport, backward, forward-based, and based for those that are interested in. But mostly specifically and important is statistically, meaning that we use a Monte-Carlo approach to deal with all the unknowns from I don't know which phase it is up to stochasticity in consumption. And so the result of this is not a point forecast of voltage and currents. No, for every equation in the grid, a probability density curves for voltage and currents. So rather than saying this will be the voltage, we're going to say this voltage is more or less likely to occur. We have to do lots and lots and lots of factors to do that. So one of the things we worked on is to make this thing also very performant and to brag a bit, because I'm actually very proud of our engineers contribute up there. If we can run this tool on our big 96 core server and into big scenarios that we can really maximally exploit analyzation, we get up to tracking 9 microseconds per power flow or 0 to seconds to calculate statistically one feed in 96 time steps. Very proud of that. But this is not useful. Well, it's interesting. It's a huge amount of data, but it's not data that you can use to do something. So we need a couple of steps to convert this down into actionable data, from data to information. And the first step is to transfer or to go from all these distributions of forms and curves to an estimate or calculation of the probability function of time for every feed that there will be a congestion. Which looks a bit like that, so that we know there's an increased risk for congestion or we're good and safe. Interesting for the DSO, but still not something that an aggregator might use, for instance. So we go one step further. Which is an optimization to calculate headroom. What does headroom mean? Well, we have X flexible devices in the field, and should they be constrained or not? Can they just do what they like and there's no problem? Or should we say, out of 50 kilowatts installed on this feeder, only 10 kilowatts can be activated to ensure that the risk for congestions is sufficiently eliminated. And that's optimization that we do. We have right now a naive optimization, not very performant, but good enough for pilot purposes. Again, speaking of good enough for the pilot, but we're already working on an upgrade, and that's my business. For the next update of the release, you'll be able to brag that you will have a convex polyhedron optimization running in your servers. There you go. Yes. And what is that result? Well, like you see that the plot, for instance, the green line or the pink line, that is a field where there is no problem, so that the headroom is as maximum, do whatever you like. But like, for instance, the orange one, which is one that is close to congestion, what you see is that the amount of kilowatts that is available is limited in function of the time to avoid congestion. This information goes to the next tooling in the chain, so that the markets, aggregators can safely decide, okay, 10 kilowatts I will use that one and that one, but as long as they save them, at headroom, we are sure that in the low voltage grids there are no problems. That tool is deployed now in Germany at INESC with the same system that we described with Dockers. We're now in the final bouts of debugging and getting everything up and running. And now exciting times ahead of us, because the saying goes, the proof of the pudding is in the eating. And the next months, I'm sure that we will encounter lots of unexpected problems that we need to solve to get this thing to do it in reasonable performance. And this is for me.
Thank you. So we have seen this approach for low voltage congestion forecasting. Now she will present an approach also data driven, but considering that we have and we can use the data from the smart metering, and we are talking about load and voltage magnitude. And so based on that, he will present a state estimation, but also a voltage control tool that helps us to estimate the flexibility needs besides detecting the congestion. Jill, please.
Okay, thank you, Clara. I'm a bit afraid that I may repeat some of the challenges that we are facing in the low voltage network, because the previous presenters were very good at mentioning them. And in fact, we have a lot of flexibility coming from low voltage grids, and we expect to have even more in the future. We are talking about microgeneration, electric vehicles, demand-side management initiatives, and so on. But the thing is, we have this flexibility in low voltage grids, but can we use it in fact? Because if we look to the low voltage grid, instead of having a very well characterized grid, we have many times an incorrect characterization or even inexistent. We don't know where the client is connected to, the topology is not updated, and so on. And also, we have smart meters, but those smart meters, most of the times only communicate every 24 hours or weekly. So the DSO doesn't even know if right now an overvoltage is occurring or not. So how can he use, in this moment, if an overvoltage is occurring, how can he use the flexibility to solve a problem if he doesn't even know that there is an overvoltage? So our approach to this, the monitoring part, and to tackle the problem of real-time monitoring, our proposal is to install a small number of smart meters that in fact can communicate in real time. And when I say in real time, I'm talking about smart meters that communicate every 15 minutes, 10 minutes, or 5 minutes. And our state estimator uses this data along with historical data from the remaining regular smart meters to build the most likely state of the system, and so on. And so we end up determining a quite accurate state of the system every 15 minutes from our tests, at least. And this comprises voltages and active power injections. And some innovations about this algorithm is that we need, in fact, a limited number of devices that communicate in real time. Full grid observability is not a requirement. If we only have a portion of the grid with smart meters, we can work with that, and it works quite well. We don't need topological information. As I said, it's an assumption that we considered from the beginning, and also it's possible to produce a conditional estimation of the uncertainty. The process behind it is, I will not get into too much detail, it can be quite heavy, but if you want to estimate a quantity in the present moment here, what we do is we build a set of explanatory variables, which is basically information that we know in the current moment, and then we compare that set of explanatory variables with events in the past. And we very simply end up doing an average of the most similar events. It's a bit more complicated than that, but there is a paper, I leave here the reference if you want to know a bit more about this state estimation. We had the chance of testing this state estimation approach in 3 real low voltage grids here in Portugal, and this is just to show you, this is the estimations over a few days for one client. So exactly a few days for one client in one of these grids, and on top for voltages and below active powers. And as you can see, the real and estimated values are quite close. So we kind of sorted out how to tackle the problem of the monitoring. So then comes the part of the control. And what we did is we explored the linearities between voltages and active powers. The basic idea is, how can I explain a voltage variation by using active power variations from the remaining customers? So we use data gathered by the smart meters, as before, voltages and active powers. We build a regression model, and basically the coefficients of that regression model are what we call sensitivity factors. And the sensitivity factor is basically or represents the impact on the voltage of a client when we change the active power of the remaining clients. It's very simple, the concept. We can build a matrix representing that, and as expected, closer the clients are to each other, higher is that impact on the voltage. Then we improve this model because some may say that linearizing and assuming the linear relationship between active powers and voltages is too simplistic model. So we improve the model to, and instead of having a constant sensitivity factor, we have a polynomial that changes according to an external variable, which can be, for instance, the active power in secondary substation or the voltage magnitude in the secondary substation. Just to consider different operating points. If you want more details, you will have to wait a bit for the month of July, where we'll present a paper in BS3 with details about this method, which also includes a very interesting feature, which is the data exchange between customers can be encrypted. So there is a privacy-preserving protocol, whether using DSO in the middle or not. And the sensitivity factors can be calculated with encrypted data, let's say that way. This is a method developed at INESC TEC, and it's protected by a patent, and it's quite interesting, so wait for the paper. This is just to show you that we can take those sensitivity factors and put them in an optimization problem, and then we can solve voltage problems, just by trying to minimize the amount of flexibility that we need to solve those voltage problems. This is just to show you that we tested. In this case, we tried to reduce the voltage. We consider a limit at 250 volts. And you can see that the voltage increased. And then we also included a constraint for the voltage unbalance between phases. We consider 2%. And then below you have the changes, the active power changes from each customer in this grid that will be required to fulfill to have the voltage within the addressable rate. So we have two tools: data-driven state estimator, data-driven voltage control. Data-driven state estimator can run every 15 minutes. I put there 15 minutes because here in Portugal it's the resolution of our smart meter, but it can be any other resolution. This can result in outputs, the most likely state of the system that can be visualized by the DSO, or it can feed data-driven voltage control. And if there is an over voltage or under voltage, the data-driven voltage control can run and try to solve using, for instance, as input flexibility offers from the market. Other functionalities that we can do with data-driven voltage control is to establish active power envelopes similar to the Headroom that Golan was talking about, which guarantee that power exchanges between medium voltage and low voltage will not cause any voltage violation in low voltage grid. There is also a paper that we submitted and will be presented next month with details about this interaction between the two tools. Regarding the deployment, each one of these applications has its own APIs. We distribute them using Docker containers and with everything that you need to run the tools. You just need a Linux environment, and that's it. Thank you.
So, thank you very much. So we try to give you an overview of our main tools. Again, I will ask you you haven't, so please configure the slide so we can also participate in the next questions. But as you configure it again, or if you haven't for the first time, I will take the opportunity, and sorry to get you by surprise, but since we have here one of the partners from the market platform, and we have also here two different DSOs, I would ask you two questions. So basically, we give you a perspective of the research institutes that we hope reflects the challenges and from the conversations and the interaction with the DSOs, we identify this as key, low voltage as a key issue for unlocking this flexibility. Do you consider it relevant in the short term, this integrating these low voltage tools in the operation? And do you foresee any additional challenge from what we identified here? So this lack of characterization, the need to forecast the congestions. Do you foresee any other challenge when talking about low voltage network operation? So maybe Mike, I ask you to speak loud because
So maybe for the urgency. Yes, of course, due to the high installation of PV, it's urgent already today. In some areas, in other areas not. If electric vehicles come, then it's the customers to decide how urgent it is. If they all decide, yes, we want to drive electric, then of course in these grids, it's needed today, tomorrow, when they decide electric vehicles. And then the rest that will come, I think, at least in Germany, would take a little bit of time. A little bit of time is 5 to 10 years. But considering how long it takes to equip low voltage grids, then I would say it's yesterday that we need it.
Thank you, Mike. So I will ask maybe Rita, I don't know if someone else, but I will ask Rita. In the Portuguese case, we are a bit more advanced on the development of the smart meters. Using that data is another story, but we are a bit more advanced, I would say. Do you have the same opinion as Mike regarding the low voltage network or for the operation?
Yeah, I think that the information that we gathered from the low voltage measure is really valuable. Also, for us to identify problems in the medium voltage network. It's like we have a million sensors distributed in our grid. It's better than people calling us, telling us that they have a problem, and then we have to go there and see if it's actually a problem. So I think that these tools are really valuable for us to be able to identify these problems. I think that the big challenge is to be able to have these tools integrated with our systems, with what we already have deployed in our networks.
Thank you. Thank you. So I will ask also the guys that are online, if you want to pose other questions in the chat, please do, and we will try to respond it. I will leave, as you write also on the chat, I will also ask Arno. So from the market platform perspective, we have been working with you closely to ensure that what we are developing is somehow integrated with you. But focusing on this low voltage network, from this market platform perspective and from more business perspective, how do you see it feasible, this idea of local distribution markets, considering the problems that we know, the low liquidity of these markets, the local characteristic of these technical problems?
The first answer to or give you my view about what you asked to my data. So I'm not working for a system operator, but inside there's lots of experience working with DSOs groups. And when we want to shift our model to DSOs, we're facing many problems, and the observability or the uncertainty is for sure one of the biggest ones. So that's something restraining the development of the markets. So I think these kind of tools are for sure enablers. So that's only, it's only for my view and our view based on what we heard from system operators. And as just so to answer your second questions, observability, uncertainties on the problem. There are some others, liquidity to be one, gaming is very big one as well. And all these challenges need to be tackled in order to enable different power markets, and that's topics we should continue working.
Thank you.
I hope it answers your question.
Thank you. So, Jill, do you have any other question in the chat?
No.
Okay, so we have some time. We have here a question regarding the flexibility, so defining the participation limits for the low voltage flexibility. And so I ask you to select one option. Should the DSO be able to enforce these capacity limits on the flexible devices, or should it procure that flexibility rather than imposing it? I think it's more or less. This was your question.
Yeah, always interesting discussion points, especially with regulators.
Maybe to add from a DSO perspective to exactly this question, takes an opportunity, both would be right. First step is, of course, market-based, but at the end, if there is an emergency, the DSO should have the capability to take action.
The secret is to define what is this emergency.
Exactly.
This is another discussion.
And so, in my opinion, we should only have the capability to enforce in several aspects, not all of them. As we may create some problems on some premises.
So I think with these answers, we are all in favor of a market-based approach with this important point. So DSO should be able, in case of emergency of the network, to change those limits if necessary. And again, in case of this emergency.
I can make a comment. I think a big discussion doing decreases, because this is only part of it. The second thing is, if the DSO procure, how to procure long-term contract, short-term bidding, there's still a whole range of solutions there.
Yeah, actually, I don't have here. So the other question is regarding this, the role of the smart meter. Peter gave this answer. So what should be the role of the smart metering? Should be only for billing and for energy consumption awareness, or should the DSO take the opportunity to improve its load profiling for network planning and operation tools, but in somehow improve this observability? But here I put it as real-time linking, so the capability of communicating in quasi-real time with these devices. Okay, I think this is also expected. So we all consider the relevance of this data. We need, and this should be a joint effort, we need to tackle the GDPR issues. Because if this is really valuable information, it doesn't make sense that we could not use it. So let's define rules to use it and to allow the use for the research, for the operation. So to improve the network operation.
Maybe what you forgot for Germany, at least, is regulation. Because in Germany, the meter data operator, the smart meter operator, is different to the DSO.
Yeah.
And that creates issues.
Particularly in those real time.
Yeah.
But at least you could use the historical data, and as we have seen, even for this.
But it's complicated to get this data. It's not only us, the customer, is it okay to get this data, to use this data, but there are a lot of more stakeholders who have to ask the way to find out who is a meter operator at exactly this point.
So in the end, the problem is from the regulation and also somehow the technical, but mostly regulation. Okay. So as a final question, I think this is a bit more aligned with comments. So we have shown different tools for different market approaches. So in the case of EUniversal, we have two distinct approaches. We have one where it's possible that the DSO selects the bids, so we do a global optimization of its own assets and of the bids that it collects from the market. On the other hand, we also developed a framework where we allow to send information, and we are not sending detailed information, technical information about the network topology, meter, the electrical characteristics. We are sending this identification of the areas and the quantity that we need to allow the markets, the external market operator, to validate and to clear the market, select the bids, and send this information to the DSO. So these are two different approaches. We can discuss about them eternally, for sure, and not get to a single conclusion. But I would like to hear a bit of comments on these two different approaches. And also if you consider the part of the validation also relevant. Maybe, I don't know, we could start here from the audience here, maybe Arno or Malik. I don't know if you want to comment a bit on this. I don't know from the online, if there are any hands raised. Arno, do you want to comment? You are, in case of the answer, you are working on the two, are demonstrating the two approaches, maybe.
So, yeah, maybe I'll start with the one I know the best, which is the approach to German people. So, I know it's good for everyone instead of having the clearing, so the optimization that's done on the market platform side, which is to kind of DSO tool. So, DSO is fetching all the available bits on the markets, and we integrate that with the network data. And using all this data, we are able to give an advice on the best leads that will solve all the issues at the lowest price. So this has some advantages. One for sure is the fact that in case there are several market platforms, let's say competing or available at the same level, we are able to with this approach to global optimization and select bids of several market platforms is that is the optimism, let's say, dispatching flexibility. So there is a discussion that could arise there. That's what about the neutrality? If it's the DSO sort of organize the markets, is there a risk? My answer is that the goal of the optimization that NSAR is providing with the setup is to reduce the cost of solving the issues on the network. So that's positive for everyone because in a way the costs for the DSO are higher, costs for the society are higher as well. Yeah, however, I don't know the regulatory framework in every country, so I think for the demonstration, that's something which should work very well. On the long run, we should.
Do you think that this approach, so having the DSO to select and somehow doing this clearing, and you have the experience of the other markets and the TSO market, so do you think this can complicate the participation of these low voltage resources in other markets, or we could find somehow to coordinate between these local markets and other markets?
The goal for us is to coordinate, sure. So using that approach, it's so possible that the bids that are not selected can be shifted to another markets. It's the multi-level approach that we've been setting up in some other projects. So for balancing purpose or congestion at high level in grids, all this is possible. But I'm not sure that one or the other approach will change something. That's the approach. Something that, however, could be different if we do the optimization at DSO level because now to the global DSO and TSO single step approach.
How do you evaluate the DSO assets compared to the flexibility offers from the market?
But I don't think we consider the demos and DSO assets.
Okay.
So
From your experience in other initiatives.
For example, on our side, we have several storage systems with energy stored there.
Yeah.
How would this energy be evaluated?
But these are of full control of the DSO.
Yes, yeah.
Okay. Because so imagine that's not allowed. So that's why I didn't know it. Yeah, then it becomes more complex.
And how do you avoid gaming? Because a user might increase their load and activate flexibility, and
Our user will increase their.
I mean, suppose a user having flexible resources can artificially inflate their load, and
As the intake gaming. That's something that is inherent to that kind of market, and will not the gaming will not be affected by one or the other
But
approach.
to answer to that question, I think it's also relevant. So at least on the Portuguese demo, what we are considering is that using the DSO assets will have no cost compared to the flexibility. And so first you consider to use the DSO assets to solve technical constraints, and then if you still have some problems, you will then mobilize flexibility from the market. For sure, they will be more expensive. At least it was our assumption.
Careful, not for sure.
Yeah.
Sometimes it is.
Yeah,
The market
in some cases,
is value for offer than the DSO assets.
Okay.
It depends.
Well, that's necessarily disagree then, because if you go to the medium voltage grid, that's a different story than the low voltage grid. Batteries, they are costly, actually transformers, and that's it, right?
No, we are considering, so we are considering only the medium voltage assets, so all PCs and so on, and we might consider also a storage device that we have as installed in the medium voltage. And so we could consider it in a dispatch for local version of the efficient. So I think
Maybe to add comment and from my side, maybe a question to it. First, the DSO is by law neutral and is responsible for reliability of supply. So whatever scheme at the end there is, if the DSO has still the power to be held liable for this reliability of supply, then everything is fine. So, and for me, that comes to my question, how can you consider in all these approaches, I have issues with the German clearing by market, what is clearing exactly meant, what is optimization, what is clearing and so on. It's another question for away, but if all these different schemes, they are there, how can you ensure transparency, not meaning putting every data in the open space, but for customers, for regulators to look into it and say, okay, I understand what it's done there, and I understand the results. If there are errors, I know what it means. If there are positive results, I know what it means. How can you make sure that it's always there, this transparency?
so.
Open question. I follow that, and that is exactly the reason why I personally need solutions where you have longer-term contracts with customers and not day-to-day bidding, which adds a lot of complexity and becomes tricky with gaming and so on. But if you would have a contract like where you would have a contract for a year or longer with the customer and say, this is what you will earn for me within these margins of constraints to switch off or do something with your client. Then you drop out all the gaming stuff, you gain transparency, you're sure that you will have the resource because that's also a problem. It will be available not if you have short-term. So it solves a lot of problems. I know that it, again, in terms of like having flexible markets and people being able to do what they do, I mean, long-term contracts have this advantage. I do see a lot of advantages precisely because of the reason that Mike.
But in the end, the DSO needs to be able to say, okay, but for tomorrow or for the next hour, I need this. And he needs to be able to calculate. And this was what we showed.
Oh, but you still need to do it. Yeah, you still need to do it.
Yeah, maybe.
You said long-term contract, you can ensure that basically will be available in a neutralized directive.
Then you say, for instance, let's take you have already exclusive night in Belgium, Switzerland, and Iceland. I have a contract with you because the reduced fee of your electricity, and in exchange, I can once, twice, 3 times per day for so many hours, for so many recovery time in between, shut the power off on.
Okay. So,
Yeah, then you're sure.
So, you can control. So, if you want to use, for example, EV, not sure if you connect it, just easily.
But that's the thing, with these things, you're sure that you can disconnect should they be on.
Yeah.
Okay. We need to discuss that payment. We will be able to do that. The people that are online cannot. I'm sorry. We have a final question, and we need them to close, please.
It's very quick. So I love the comparison that you made between PVs, PV penetration, and EVs. You said this is more on consumers. Do you think the same applies for electrification of transport in general? So public transport, electric buses, increased reliance on small, electric scooters, etc. You're seeing this in metropolitan areas more and more. How do you see this with the use of
From the connecting for me is how the capacity of connecting is different. If you have buses, public transport, then you have a large hub or 2, 3 large hubs that are in a high voltage system. That is a little different. The impact is different than the distributed electric vehicles at every household in the streets and so on.
I understand there are models like with one route charging, Like sometimes they are more economically efficient at on-road charging, with flash chargers.
But in this case, to be honest, I believe in a separate infrastructure to make sure.
So you would rather separate them completely than deal with the complexity?
Okay, we really need to close. So in 5 minutes, we will have the joint session where we will present the main conclusions of the 3 breakout sessions. So I invite the people that are online to do a small break and then join us at 4:15 in the main room. So thank you very much for participating. I hope that you are that is as enlightened the approach that we are developing. Thank you very much.